Hello, hi, good evening, everybody. Hello, good evening, and welcome to today's tutorial on urban services planning. I hope my screen's visible and I am audible to everyone. Can you confirm? Yes, no, no? Okay. Hello, am I audible? Any reaction? Okay, maybe not. Hello, hello, good evening. Okay. Hello, good evening. Am I audible? It looks like I am, but can I have some response from someone so that we can start? Okay, someone's raised a hand. Yeah, please go ahead. Shal, you want to say something, or did you raise because I'm audible? Anything in the chat? Okay, thanks. Thanks for that confirmation. Yeah, thank you. Yeah. Great. So we can start today's session. So today we'll be discussing about the content of week 5. Before we begin, there was one doubt which Suranjana had asked last class about uh, getting a sample for testing the composition of waste. So I'll just start with that. So this was that slide. So I think the doubt was on do we stop at 1/8 or do we take 10 kg? I think that was a doubt. That time I didn't look into the PPT, so I didn't understand the question properly. So the answer is that you stop at 10 kg. So this 1/8 was to say that it becomes 1/4, then you reduce it to 1/8, so then it becomes 1 by 16. So it just keeps going until you have around 10 kg. So the desired size is 10 kg, but it's not like a hard and fast rule that it has to be 10 kg, but something around 10 kg would be a good sample size. Was this a doubt or am I getting this wrong? Suranjana? Okay, so I guess there's some network issue. Fine. So we'll come when she's back, maybe she can ask. So with that, let's begin today's discussion. So today in week 5, mainly we discussed about different waste collection mechanisms and transportation mechanisms, routing, and how do we plan for waste disposal and uh, how do we plan the whole system in which it can be collected from the source and then taken to the landfill. So these are the topics which we discussed. So we discussed about different types of waste collection systems, primary, secondary, tertiary. Then we discussed who are the generators and how do we collect it from the generators and what are the criteria that we use. Then we also looked into different transportation methods on how do we collect the different vehicles, what are the vehicles suitable for primary, secondary, where do we plan transfer stations or tertiary collection systems. So what are the characteristics of these stations and what are the factors that we consider while planning these transfer stations. We looked into some case studies. Then we also went into more details on how do we plan a door-to-door collection system and what is the if it's other community bins, what is the frequency of how they should be planned. We also looked into the transportation mechanism. So this was one part, and then the next part, which we had two lectures, was mainly on how do we plan the vehicles, what is the vehicle routing, when there are multiple vehicles, how are the routes optimized so that with minimum distance and minimum time we can uh, touch all the points. So we discussed different route choice problems on that, different algorithms that can be used for this. Then we also looked into solving these so some of the techniques like traveling salesman problem we looked, but we did not go into the details on how it can be solved, but we learned these terms and these are different algorithms by which these problems can be solved. But in today's discussion we will look into a vehicle routing problem and a traveling salesman problem also, so that we get an idea about how these can be solved. Right, so with that, let's get started with today's questions. Okay, so the first question is dash are provided when the distance between the secondary storage and disposal site is more than 15 kilometers. Oh, sorry, the slide didn't change. One sec. Right. Uh, yeah, so we are on problem 1 right now. Dash are provided when the distance between the secondary storage and disposal site is more than 15 kilometers. Somebody says A as the answer. Uh, okay, let me just, am I not full screen for all of you? I'm full screen, right? Yeah. Okay. Yeah, okay, I'm full screen now. Fine, good. Um, yeah, so somebody says A, motorized, okay, someone said A and somebody also said motorized vehicle. Okay, great. So, yeah, so here we are talking about distance between secondary storage and disposal site. So what are the different types? So we learned primary storage, secondary storage, and then finally imagine we have a disposal site. So something which is in between is what is asked. So let's revisit on what we discussed about what was a primary storage. Primary storage. So a primary storage or a primary collection system is when we directly take it from the source. So we have the source, and then whatever is taken from the source comes as primary. And from primary can either deposit it in anywhere, like it can be a storage facility, it can be a storage truck, or it can be, even if you can take it to a bin, or it can even be the disposal site. But the idea is that if you start from the source, then it's primary. Then from this intermediate storage, if you take something, then that becomes secondary. And that secondary again can be deposited in any of these facilities. So either it can be a disposal site also. Now, if there's something between the secondary and the disposal site, an intermediate storage, and then you're using a system in order to take it from there, uh, what is that? So here, what is asked is Dasha provided a distance between the secondary and disposal site if it is more than 15 kilometers. So the answer is A, transfer stations. I think Shweta has correctly said answer is transfer station. So if the distance is more than 15 kilometers, generally we say that we need to give a transfer station, or that there has to be an intermediate facility, so that there's no, yeah, so you need an intermediate stop. So that can be a storage facility. It can be a community bin, or it can be any facility, but that becomes a tertiary, or you have a transfer station, and then this becomes a tertiary collection system. From here, when you collect, it becomes a tertiary collection system. Now, this 15-kilometer again is a very what do you say, general rule that we follow, and it's not a hard and fast rule, that it's not like for every 15 kilometers we need to give another transfer station. There are several other factors which are considered while deciding whether a transfer station is to be implemented or not. For instance, these are the this is what we discussed in the slide at a later part of the lecture. We discussed that transfer stations are provided under a certain condition. And what is that condition? The condition is that the cost of direct haul, by direct haul, we are talking about directly transferring it to the disposal site, the direct haul to the dispose site or treatment facility, if that cost is greater than the cost of the secondary cost of the haul of the secondary facility to the station, additional haul in storing this, and then the cost of the infrastructure and the transfer, plus this modified infrastructure. So all this together mainly includes the cost of installing that transfer station, or implementing it. So you have a transfer station, you need certain vehicles coming from the secondary storage to the transfer station, then from the transfer station to the disposal site. So all this put together, if this cost is lesser than the cost of directly putting it in the disposal site, then we give a transfer station. But usually we provide for around 15 kilometers. So the rule of thumb is taken in such a way that if the distance is more than 15 kilometers, mostly this cost will be higher. So, this cost will be lower. So since this cost is lower, then we go for a transfer station. So this is again just a rule of thumb, but like before installing a transfer station, we look into other factors also. So coming back to the question, the answer is transfer station. To look at the other options, large capacity vehicles. So now this again depends upon the quantity of waste that's being generated. So for this one, that doesn't match. Motorized vehicles. Yeah, so if there's a lot of distance, you need motorized vehicles, but this is not the 15 kilometers is not the condition for that. Then curbside stations, again, this is mainly used when the streets are narrow, or you have a curbside station where people come and put the waste in the curbside station because of lesser connectivity in that region. So that again is not suitable over here. So yes, so let's go to the next question. Match the type of waste collection system for individual generators with its likely characteristics and choose the correct option. So we have P, communal storage and collection, Q, door-to-door collection, R, curbside collection, and S, block collection. And characteristics: generator delivers waste at the time of collection. Two, generator has to walk a certain distance for waste disposal. 3. Collection from each generator or premise. And 4. Waste is kept outside the house and the bin is retrieved later. Okay. So let's go the first one, communal storage and collection. Which of the option matches that the best? Okay, somebody says C as the answer. So I'm assuming that you're talking about option C. But before that, let's go into different P for P, which is better. One. So Shweta says one. Generator delivers waste at the time of collection. Okay. So communal storage, the generator is not delivering at the time of collection, right? So for instance, you have one region, you have certain residences located over here, like there's a road, there are certain residences here. Now you have a community bin over here. That is communal storage and collection. So you have commute. So for each region, for each locality, there's a community bin. So which means people from this region will come and dispose their waste in this particular community bin. So the answer to this is generator has to walk a certain distance for waste disposal because it's not readily, it's not very close to their house. So they walk a certain distance and then they deliver it. Now the other one, for instance, block collection. Since one has Shweta said one, I'll just go to block collection. So block collection, what happens is a person comes to collect the waste. So again, it's similar to a communal storage, but the difference is there is no storage. The person is coming, and then when the person comes, people will come and then dispose the waste at that time. So usually he comes and blows a whistle or gives an indication that the person is there, and at that time people will come and deliver the waste. So in that again, the person has to walk a certain distance, but the option one, the generator delivers the waste at the time of collection, is more appropriate because it's only at that time of collection. There's no 24-hour service. You're going and giving only at that particular time. So this becomes this and this becomes this. Yes, mistake two is C. Okay, yeah, that's correct. Let's come to that. So that's done. Now we have door-to-door collection. So that is easier. Door-to-door collection from the generator and the premise. So that we know, door-to-door collection. And then finally, we have the curbside collection where the waste is kept outside the house and the bin is retrieved later. So that also we've seen, like if you have a street, we have along the curbs, we have waste bins kept. And then a truck comes and then using certain mechanisms, this entire bin is taken and then the waste is tilted and then it's kept. So people retrieve the bins later after keeping it over there. So that works out to option C. Yes, option C is the correct answer. Shall we proceed on to the next question? Okay, question 3. Choose a mechanism that is utilized in managing the information system for waste collection and transportation. A. Geological positioning system. B. Radio frequency identification. C. Geographic radio services. D. General information system. Any guesses for this? Uh, S. C. Okay. Okay. Geographic radio services. Anybody? Any other answer? So somebody says geographic radio services. Somebody says D. Okay. General information system. Fine. Okay. So this is interesting. So I'll directly go to the answer over here and then come back. So the answer is radio frequency identification or RFID. So how RFID works? So RFID, it's a very simple. So you have a chip, and then like probably it's in a card or it can be put in anything. So sometimes it's in a keychain or it's in a card. So the most common one is which is seen in a card, and the very good example of RFID tags is what you have in your hotels. If you're checking into a hotel, you get a card as a key. So this card is equipped with an RFID chip inside that. So when you tap it on the door, it opens. So that's an RFID tag. Another good example is what you have in your in the cars where you have the automatic billing system on the cars where you go through a collection booth. It automatically takes the money. So there again, there's an RFID tag. Yeah, fast tag. Yes, fast tag is a good example for that. So you have the chip inside these FASTag cards which are put and then the money is deducted. So this is RFID where you can use this. There's a chip and then you can scan the chip. So now how this is used in waste collection and transportation is that usually when waste is collected, in order to mark that waste has been collected from this particular locality, they tag they use this chip, and then that gets automatically tagged that okay, from this locality waste is being collected. So then you have an idea of which all locality it's already been collected and at what frequency it's been collecting. So it's an automatic monitoring mechanism where you just tap it. There are other smart mechanisms also which are coming, where RFID tags are used in order to uh, RFID tags are incorporated in smart waste bins. So these are very new projects which are coming up. So in IIT, in our IIT Kharagpur, in one of the labs, a smart waste bin has been made. So what it has is, it's a waste bin and there's an RFID tag, which on reaching a certain, so there is a sensor also. So it automatically looks at when the waste bin is full, this RFID tag can sense that and then send signal to a location where, so there are other chips also inside it which send signal to the main system, which says that the waste bin is full, it needs to be emptied. This has not been implemented. I'm saying that such smart systems are also coming. So when they're coming, they can again scan this RFID and then now they know that this has been emptied. So for the next frequency, it gets ready for the next emptying rate. So these are some of the uses where RFID, so these ones which I said, where after the waste collection attacks, these are already implemented. These are some of the new innovative methods which are coming up also. Now there are other systems also which can be used, like we discussed about GIS. So I'm sure somebody mentioned general information system, maybe under the assumption that this is GIS. No, GIS stands for geographic information system. So it gives us in a complete region. Given the region, you can have certain uh, tables associated with the region. So again, the information from this RFID tags can be input into these GIS systems, where under each region, you know what is the frequency, what is the weight of the waste which was collected, what is the composition of waste. So all that data can be stored in a map, in a spatial map. So that's a GIS system, or a geographic information system. Now, in order to find this, we can have certain GPS mechanisms. So GPS stands for global positioning system. So you have a global positioning system. So here again, to confuse, the option has been given as geological positioning system. Had it been global positioning system, then that also becomes a correct answer. So GPS is a correct answer, but since the expansion is given and it's given as geological positioning, it's not the correct answer. So using GPS, we can locate different regions, what's happening. So it gives a location information. Then there are other GPRS services also, where through which we can communicate, like from the given region, you can communicate, you can send packets across the regions. GPS only gives a location, but whereas GPRS, it allows communication also. So that's also another mechanism which is used. So the options are a bit confusing, and the answer to this question is radio frequency identification, which is the RFID, which is used. Okay, so we'll proceed on to the next question. Problem 4. The process of removing segregated or unsegregated solid waste from the source and transferring it to the storage depot is called dash. Primary collection, secondary collection, tertiary collection, treatment of waste. So I think we've already discussed the answer to this. So A, primary collection. Yes, it is primary collection. Why? Because we are talking about source. Segregated or unsegregated, it doesn't matter, but we are taking it from the source and then we are transferring it, whether it's to a storage depot, whether is it to the recycling plant, or whether it's to the final landfill area, wherever it is, it doesn't matter. But the only highlight is that it is taken from the source, then it is primary collection. Right. Let's proceed on to the next question. Question 5. Selection of vehicle chosen for door-to-door waste collection does not directly depend on which of the following? A, sorry, topography, B, collection frequency, C, type of waste treatment, and D, building density. Yeah, so any answers for this? C, collection frequency. Okay. The vehicle chosen does not depend upon collection. Sorry, C, type of waste treatment used. Okay. That's a possible answer. Anybody, any difference of opinion? Any other answer? Okay, so yeah, so that is the correct answer. The type, the waste treatment, it does not depend upon the waste treatment used. Why? Because waste treatment comes after waste collection. So you have a door-to-door collection system. You're taking it, you're giving it to a storage region where it's segregated, it's sorted, and then after that it goes into different waste treatment based on the composition of the waste. So the vehicle which is used does not depend upon the treatment, which comes after the collection. It does not depend upon the treatment. So yes, that is the correct answer. Now let's also look at how the other factors influence. For instance, topography. So based on the by topography, we are talking about the land characteristics or the terrain and the region. So based on the region, the vehicle also needs to be improved. For instance, if it's a sloped region, a handcart might be very difficult to carry along. So you need a motorized vehicle in that region. So it depends upon the topography. Then collection frequency. Now the capacity of the vehicle will have to be altered based on collection frequency, because if it's collected for 24 hours, then the imagine we need capacity x, and if it is for a 24-hour collection system, if it is made into 48 hours, then we need 2x, because the people will have to store their waste for a certain time and then they'll have to give it off after 2 days. So which means the quantity of waste is also going to increase, and the capacity of the vehicle will also have to be changed based on that. So which means that influences the vehicle that we are choosing. So this does not influence. Now building density, this also influences, because more number of people in a region, if it is more densely located, it also means that more number of people are residing in that region, and the waste generated will also be more. So which means this also influences the capacity. So both collection frequency influences the volume, building density also influences the volume, and hence this influences the vehicle choice. Right. So let's proceed on to the next question. Question 6. Match the vehicles or the equipment used in the waste collection with their most likely configuration or description and choose the correct answer. So first one, we have hand carts, rare loading compactor trucks, are light commercial vehicles for door-to-door collection, S places. And the description is used to transport waste from storage depot to treatment or disposal sites. Two consists of four openings, two on each side. Three mostly used for construction and demolition waste transportation, and four suitable for narrow lanes. So let's go first one, hand carts. Where hand carts suitable? D, yes, handcards are suitable for this one, narrow lanes. It is more suitable for narrow lanes. Fourth option is correct. Now Q, rare. Yes, very good. Four. Now Q, rare loading compactor trucks. So rare loading, you're mainly talking about compactor trucks. Where can that be used? Trans from storage depot to treatment, or for construction and demolition waste. So one, yes, everybody says one. So now why this is useful? Because now you have a storage depot and then you're going to the disposal site. So there's a lot of waste in the storage depot. So now you can, in the compactor truck, we can compact it. In the rear loading compactor truck, you can compact it and carry maximum amount of waste, because in this region mostly the sorting is already done. So when it's of the same composition, it's more easier to compact. So these rear loading compactor trucks can be used in order to take it to all the treatment or the other disposal areas. Very good. Now light commercial vehicle for door to door collection. 222 consists of four openings on each side. Yes, it consists. So that one, so we might have observed. So in the truck, there can be certain compartments, and then these bins or whatever is taken from different regions can be put in different compartments. So that's why they're talking about openings on either side. So if this is one side of the truck, like imagine the truck is like this is one side, it can have two openings over here, it can have other two openings on the other side, the compartment which is kept, it can have an opening over here. So that's the commercial vehicle which is used for door-to-door collection. Then we have dumper places which are used for construction and demolition waste. So dumper places are something like where you just have the cart, and then you have certain hands to bring. I think I have an image over here. Yeah, so I have these images. So yeah, so these are rear loading compactor trucks. So it looks something like this, where you can put it and then compact it and then take it off. Now you have the light commercial vehicle. So it's something like this with a tipping floor, which means it can be tipped or rotated. So in the next one, I have the image of do I no, okay, that one's not there. Yeah, so there's also you can put certain like it can be opened on all different sides. Now this one is the dumper placer, where you can place different blocks. You can directly place it onto that. So let's come back. So that works out to which option? Four. Is it option D? Q is no, P is 4 and Q is 1. Yeah, option 4. I think some D. I think somebody already answered that. It is option D. Yeah. So let's proceed on to the next question. Problem 7. As per CHPEO 2016, okay, choose the standards that they say true for a city with a population of 5 to 10 lakhs. So 75% door-to-door collection by light commercial vehicle in primary collection, 55% door-to-door collection by compactor trucks in primary collection, 100% door-to-door collection by tractor or light commercial vehicle in primary collection, door-to-door collection using hand carts and tricycles only. So remember the manual? Anyone? So any guesses? D, okay, door-to-door collection using hand carts and tricycles only. Okay, that's a wild guess. Uh, okay, anybody, any other guesses? Okay, let's visit what we saw over here. So, yeah, there's a correction. It is CPHEU. In the question, it was written CHP. So there was a small. Okay, somebody says A also. Yeah, your guess is correct. A is the right answer. So, yeah, so A had meant in A, it was 75% door-to-door collection by light commercial vehicle in primary collection. So for 5 to 10 lakhs, it is 75% door-to-door collection with light commercial vehicle for primary collection. Now, if you're looking at other processing and recovering, in that, so after the secondary collection, when it comes to there it can be 100% door-to-door collection of processed and decentralized sites. So from all the decentralized sites, 100% should be collected. So, but here mainly we are talking about primary collection. So it is 75% door-to-door collection for 5 to 10 lakhs. So yes, good, your guess was right. So this is directly from the standards. Let's go to the next question. Which of the following does not define household waste characteristics? A, quantity, B, bulk density, C, compressive strength, and D, composition. So we are talking about characteristics of household waste. Quantity, does that affect? Okay, somebody says C. Yes, let's come to that. Quantity, does that affect? Yes, based on the quantity, we'll have to plan our the based on the quantity of each characteristics, we'll have to plan our waste management system. So yes, household quantity defines waste characteristics of a household. Bulk density, does that influence? Yes, yes, yes. Bulk density also influences because based on the density, we'll also have to look at the volume that would be required. So bulk density influences. Now compressive strength. Now compressive strength does not. You're right. The answer is right. Compressive strength does not. Why? Because compressive strength is essentially the ability of a material to undergo compression. So, for instance, if you have a block of concrete, so concrete, we always do a compressive strength test for concrete before it is used, where from both sides pressure is given, and at what point or at what under what stress does it start to break. We look into that, and then that is given as the compressive strength of that material. Now, for waste, that doesn't matter because, yes, we need to compress it while taking it from the disposal site to a waste treatment. But you're not looking at the compressive strength. You're not looking at at what point it starts to break. So, in the collection mechanism, when we are taking from the household level waste characteristics, the compressive strength does not matter. Now comes composition. Yes, composition also matters because eventually we'll have to segregate and then we'll have to plan what is the waste uh, treatment facility that needs to be provided. So for all that, when we're looking into the waste characteristic, composition also matters. But compressive strength does not define the characteristic of a household waste. Very good. So let's proceed on to the next question. Question 9. Which of the following statements are more likely to be true regarding door-to-door waste collection system in a typical Indian city? P. Urban poor and slum areas receive minimum solid waste collection services. Q. Low income group areas receive the maximum solid waste collection services. R. Collection is extremely inefficient in middle income group areas. And S. Collection rate is extremely efficient in high income group areas. So let's go option by option. First one, urban poor and slum areas receive minimum solid waste collection services. That's a correct statement. Yes, no? Yes, yes, that's a correct statement because in the poor region, because of lack of connectivity, lack of road networking, all that, the solid waste connection services are also minimum. So the urban poor and slum areas receive minimum solid waste collection services. Now, Q, low income group areas receive the maximum solid waste collection services. So now this again is contradicting the first statement. So this is a wrong statement because uh, for low income areas, again, you're not prioritizing for low income areas. So usually it's the other way. High income areas receive maximum solid waste collection because again, because they're willing to pay more, whereas low income region, they might not be willing to pay for the solid waste collection services. And as we have discussed, uh, usually people need to pay for workers to come and collect the waste and then take it for a door-to-door system. So they do not receive low income areas do not receive any priority over there. So this is a wrong statement. Now, our collection is extremely inefficient in middle income group areas. Now, that's also a wrong statement. It's usually inefficient in low income, not in middle income. In low income, it is very inefficient because of several reasons, like as discussed, because of connectivity issues, because of their lack of willingness to pay, and also certain of these slums are not even registered. There is no in the plan or in the municipality plan, these regions are not even identified at certain cases. So in that case, the focus is not given to this region in order to collect waste from these regions because they are unauthorized settlements. So because of this, collection is extremely inefficient in these low income group areas. Now, S, collection rate is extremely efficient in high group areas. Now, that is a correct statement. Yes, because in high group areas, they, as discussed, they are ready to pay. They have better facilities around. So, with all that, the collection rate is more efficient. So, that works out to P and S, which is option D. I think somebody had already answered that in the chat box. Yes, option D is the correct answer. Yeah, so this is what we discussed in our door-to-door collection, where we discussed what are the problems in low-income groups. So it is sporadic and inefficient. Now, service is limited to high visibility areas. So as discussed, there are certain regions which may not even be in the visibility of the municipality or corporation. So the low-income region. So those are never considered while planning a door-to-door collection system. And yeah, so now improved service, increased collection, larger vehicle fleet and more mechanization. And when it comes to high income group, even compactor trucks and highly mechanized vehicles can be taken. So the road network is also so good such that such vehicles can also be taken. So proceeding on to the next question, problem 10, dash denotes distance and dash represents time restriction in routing and scheduling for solid waste vehicles. Option A, link and node. Option B, link and network. Option C, node and link. Option D, node and network. So what represents distance and what represents time? Any guesses? So let me just draw. So we have something and then we have something. So what is that? Time restriction in routing. So somebody says B, link and network. Okay. B. Okay. Two people say B. Somebody says A. Okay. So by default, this entire thing, for instance, we have something like this. This whole thing is called a network where you have certain nodes. These are all nodes. And then we have certain links. Now, nodes mainly talk about what is the time taken to come from this point to this point. Like if this is A and B, in node B to travel from A to B, what is the time taken? So that is usually mentioned over here. And this distance, so whatever is linking node A and node B, that becomes a link and that denotes the distance. So it's link and node, which somebody has answered A, it is link. So link denotes a distance that is from A, and this one, a node represents the restriction in routing and scheduling solid waste vehicles. So from A to B, so mainly, again, it mainly talks about the restriction. So node means those are fixed junctions or location we can take. Or for instance, if we have certain bins located in certain regions, now imagine bin B is located over here. Now bin C is located over here. So if it's a region with community bins, now all those becomes our nodes. Now, and in nodes, we usually look at how much time is taken from to come from this distance to this distance. So that is also put inside a node. Does node restrict time restriction? Yeah. So by time restriction, we are mainly talking about when you're doing solving a network analysis program, solving a network, it is on the node that we look at what is the time taken to travel from this region to this region, how much. So that calculation, so we learned about different algorithms by which we can do. So in those algorithms, we'll be writing it on the node. So yes, if you just yeah, this can cause some confusion, but it cannot be anything else. So let's go by eliminating the options, other options. It is definitely not a network, because network is all the whole thing is called a network. It's not a link. Again, it's not a network. So the best option over here is it is a node. But if you specifically ask, does it represent the time restriction? No, it doesn't. But when we're doing an algorithm, we always put it at the node, what is the type. So a node can be an answer. So again, in this one, we're going by the best answer and then taking it. The definition of node is not a region which denotes the time restriction. No, that's not the definition of node. Node is a specific region where it is there, and link is what connects between different nodes. Yes, so your doubt is very much valid, but for this, the answer is link and node. Right. So let's proceed on to the next question. So and this is we'll have to solve something. So a network is given. So this the whole thing which is given as a network. So again, going back, we have Q, P, bin B, bin A. All these are different nodes, and then the links between different nodes are also given, which again talks about the distance or time which is given in the link. Now we've been asked to find the shortest route sequence using Dijkstra's algorithm. So let's different options are also given. So let's first look at what is this algorithm, how we go about it. So I'll give you the algorithm. We've discussed this in the lecture, and then I urge you all to solve it yourself, and then we'll come back and discuss. So the algorithm goes that you take any two pair of vertices. So okay, before we start with the algorithm, there's a condition that it solves single pair, single source, single destination shortest path algorithm. So let's look. So we have a single destination, so single source. So we are starting from the depot, and we need to collect from bin A and bin B, and then go to the landfill site, and then deposit it in the landfill site, and then come back to depot. So so you have a single source and single destination. You're again coming back. So it works for single source, single destination. So this can be used. Now, the algorithm goes that first we take any vertex, and for a given vertex, we assign it. So the vertex from which we are starting, that is always set as 0. And the distance to all the other vertices, we give it as infinity. And then, so so from that infinity, then we look at which are the two vertices which has the minimum distance. So we look at all the distances, and then the minimum distance one is chosen. So we go to the unvisited vertex, and then for the smallest known distance, we will take that one. So for instance, if I'll just give you an example, Q and P. To decide whether we want to go to Q and P, we know that to come to P from the depot, it only takes 2. So that's minimum. So we will go to this one. Again, this may not be the answer for this question. I'm just not looking at, I'm not looking into this side at all. Just by looking at this much, I'm saying that this is the method in which we proceed. And then so like that, we look at all the unvisited neighbors, and then we decide on what should be the minimum distance, and what should be the, so while looking at this, we also look at the overall minimum distance. So for instance, coming back over here, if I'm taking as bin B, you look at all the options to come. So it's not just in Q or in P, but you look at the whole network or multiple nodes, and then you look at what should be the minimum distance to come there. And then you keep repeating the steps, and finally we get the, after we finish all the unvisited neighbors, we get the total minimum distance which needs to be taken. I mean, this explanation, when you do the problem, it will be very clear. So with this particular question, the requirement is that you need to visit bin A and bin B. It is not necessary that you need to visit all the other nodes like Q and P. It's not necessary you need to visit those, because those are just junctions, and even if you don't visit them, it's okay. But bin A and bin B needs to be visited, and the landfill site needs to be visited, and finally you need to come back to the depot. So I think you can take 2 minutes, and if someone can solve it and then tell me what is the answer, it would be good. So I'll just leave this question on. Yes. But yeah, more than this, I felt the other one would be easier if you just look at it and then. Hmm. Yeah, right. Yeah. Okay. Yeah, yeah. Because this is a question, right? So yeah. So you can tell me which is the route, and also tell me what is the cost. So all this, what is written over here is the cost. So it can be the distance, it can be the time taken, whatever it is. So since it's not mentioned, we're just taking it as cost, and we also need to minimize the cost. So the path with the minimum cost will be the one that we will be taking. So I think that is the next part of this question, question 12 also. What is the cost? Okay, somebody says D24. Depot to P to landfill site to bin A to Q bin B. Depot to P to landfill site to bin A to Q to bin B to landfill site again. Okay. So you're going to landfill site twice, and 24. Right. Okay. Let's wait for others also to come back. Meanwhile, you can also check. There is a more optimized method. You can check that, cross check that once more. So in this one, A and B, the intermediate P, Q, and R is not given. But that doesn't mean it's not there. It's there. It's going to some P or Q or something, but it's just not given in the option. If anybody's getting any different answer, you can post. Shall you may just check that once more. C29, okay. Somebody says C2. Okay, Charlotte will say C29. But 29 is more than 24, no? So which means it's your D is a better answer, right? But no, we get an even better answer. A20, okay. Somebody says A20. Is 20 the least? Okay, okay. So let's B23. Okay, if you do B, you get 23 also. Okay, so very good. So I think we have worked out everything, whichever path is taken, everything is worked out. So Shweta says A20 and B23. Both are correct. So the answer to this is C28 and D24. Yeah, D is 24, C28 or when. Okay, let's see. So again, we need to choose the one with the minimum, right? So you need not work out everything and then check. Uh, I hope you did not go by checking all the options rather than that following the algorithm. So let's follow the algorithm and see. So the first one, so everything is initialized as infinity now. I think I have, yeah, so this, I'll solve it here. So everything is initialized as infinity, infinity. We are just taking two pairs. So let's say now bin A, sorry. So we have bin A and bin B. Now, because these are the two regions which we eventually want to reach, so I'm taking bin B. So this is the pair that I want to find, depot to bin A. Excuse me, yeah. So depot to bin A, one method is I can travel to P, so that becomes 2. I can then travel to bin A, so that becomes 2 plus 4, which is 6. Now another method is I can travel this way, so that becomes 5 plus 4, which is 9. And I can also travel this way, so which is 4 plus 4 plus 4, 8. So among this, yes, 6 is better, so I can choose 6. But I'm just leaving it there. Now, parallelly, I'm checking B's case. So now this infinity of B is gone. Now to depot to B, so first one, the typical one, so it is 5 plus 4, which is 9. Now, is there any other method? I can also travel this way, P, Q, and R. So that becomes 2 plus 2 plus 4, which is 8. And I can travel this way, which is 2 plus 4 plus 4, which is 10. Is there any other way to travel? Yeah, then the others involve going through landfill site and then coming, which by the look of it itself, so let's go through the landfill site and then see. We'll have to look at all the options by which yeah, you can travel via landfill. It's not an issue. You can travel via landfill. So that becomes 2 plus 5 plus 2, so that's again 9. So yeah, so we have different. So in this we know that we have 8 over here, which is the minimum. So now among 6 and 8, 6 is minimum. So our immediate tendency would be to go to bin A. But now from bin A, we also know that we need to travel back to bin B, or we need to go eventually go to bin B. Now, if you're doing that, what happens is it increases the, so now we'll have to look separately. So A and B individually we've got. Imagine we are traveling to A first. Now, if that is the case, we'll see from A to B, what is the strategy. So from A to B, we have to go. So let me erase off what is there over here to avoid confusion. Yeah. So coming back now, A to B. So A to B can be traveled this way. So which means it's 5 plus 2. Then you can also go this way, which is 4 plus 4, which is 8. So you have two methods of traveling from A to B. Now, this will involve plus 6 also, because to travel to A, it was 6, right? So eventually this will be 14 and this will be 21, right? No, B to A to B. Yeah, sorry. Yeah. So this one would be, um, yeah, 14 again. Same thing. Okay. So yeah, so even this comes out to 14. Now those are the two methods to go. Now let's see from B to A, what is the method? So B to A, initially it was 8. So 8 is already there, plus whatever we are adding on, again the same path. So we can say that this is the shortest path because we know that 7 is less than 8. So I'm just taking this one, this path. So which will be plus 7. So that is 15 to come back over here. Now again, now we need to, so if this is the case, now in this one again, so you need to check everything. 7 plus 6, 7 plus 6, yeah, 7 plus 6, 13. Yeah, sorry, marked it wrong over here. 7 plus 6, 13. Yeah. Now, the next one would be if you want to go from bin A. So now you're in the second one. Okay. Now for both these cases, you again need to see. So here you have ended up in bin B. Now you have in bin A, you travel to bin B. Now from bin B, you need to travel to landfill site. So what does that work to? So so that would be existing. You have 13 or 14, whatever. So I'm taking 13 plus you'll have to take, sorry, you'll have to take this route 2 plus 5. That's the shortest route compared to all the other routes. So 13 plus 5 plus 2, what is that? 20? Yeah, 20. 20, correct. So that's already 20. Then if you want to go back, so I'm just recalculating the whole thing over here itself. You want to go back to depot, so that becomes plus 4, which is 24. So this is what is going to happen. Now imagine you're taking the other one. You're going to B first, and then you're going to A. So now from A, you can go to B in one go. So it is 15. So 15 plus 1, which is 16, plus 2 to go to P, plus 2 to go to depot, that will become 20. So in 20, so if you're choosing the path on depot to B to A to landfill site to depot, we are getting it in 20. So which means this is the shortest path that we would be taking. So yes, so the answer was right. Option A is the answer, where we go from depot to bin B first and then to the landfill site and then to depot. And the next question is, what is the time taken to travel? So this whatever was given was a time. So the time taken to travel would be 20. Option B. Any doubts in this question? No, okay. I think a very similar question is there in your assignment also, but just be careful because the values are different. The entire path can be different because the diagram may look like this. For instance, this might look like a shortest route, but we know that this is shorter because this takes 5, this takes only 4. So the diagrams can be misleading. Just pay attention to the numbers and follow the steps, you'll get the answer. Right. So we are proceeding on to the next. Okay, somebody is raised. Yes, but you may ask your question. Hmm. Yeah. Yes. Correct. Correct. Yes. Yes. Simple answer. To confuse students. That's it. So, no, I mean, these questions happen this way. Now, yes, that's a very good point. No, correct, correct. Right. Yeah. So yeah, that's a very valid point which you have raised. So yes, but these questions appear this way, this the a similar way in GATE exams also. So again, so the idea is that if we are clear that it is impossible to go directly to this way, like if you know that we need to follow the network, we would also know that there are certain steps which are missing in this. Now, yeah, so it is. The options could have been given the other way. So now this was the same question which was, I think it's there in this time's assignment also in this format, previous assignment also in this format. So yes, the other ones could have been given. Here it's again these things are also given. There is nothing missing as such. It's just to say that what is important is that you need to cover bin A and B and you need to go to the landfill site. It doesn't matter whether you go to P, Q, or so these over here, these are actually redundant. It doesn't matter what which whether it's shown or not. Correct, correct, correct. Yeah, 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 yeah. Perfect. Yeah, that's the ideal situation, but everything's not fair, right? So you might come across these type of questions also where something is given to confuse. So yeah, there is a lack of consistency and that creates some confusion. But if you're clear that this is the path or this is the way which we solve it, then we will be able to come up with the correct answer. If the bin number is not mentioned, should we consider it? No, so because so that's why this is it's highlighted. These are the only two regions where bins are there. Uh, yeah, nothing else is mentioned in this question. Yeah, these are the only two regions where bins are there. These are just junctions, the different paths that can be taken. Say only one bin number is mentioned. Okay, so which means this is shown in yellow, but nothing is shown. Then there might be something wrong with the question because uh, here both color and this one is shown. Actually, yeah, in that way the question is because it should have been mentioned in the question clearly that you need to collect from bin A and B and then go to the landfill site. So that will be clear in the question, which are the ones which you need to consider. The other ones PQR, if you need to go to all the nodes, again that will be mentioned, like go to all the bins and touch all the nodes also, like those will also be mentioned in the question. So this one, yeah, I think the question is just given in this way because mainly because the same thing is there in the PPT in the lecture, so maybe that's why it was omitted, but if it's in the actual question it would be there. Then need to follow the process depot to bin, landfill, and then depot. Yes, you need to follow the process depot to bin, landfill, and then depot. Correct. Okay, so let's proceed on to the next question. Which of the following statements are true regarding vehicle routing for solid waste management? P. If the outcome of a traveling salesman problem is 1, then it is a vehicle routing problem. Q. Vehicle routing problem gives a set of optimal routes for a fleet of vehicles. And R. Traveling salesman problem gives a single route that visits each point exactly once. S. Traveling salesman problem shows the maximum travel distance and cost for visiting fixed locations. So, okay, so we are mainly talking about traveling salesman problem. What is a traveling salesman problem first? Excuse me. So we say that if we have A, B, C, D, E, if we have certain network like this, we are assuming that like there are different, like it can be this way, this way. So we are assuming that a salesman needs to travel to all the locations and he optimizes his path before traveling else. So he decides, so he has a complete freedom to decide where he's starting from, where he's gonna end, so that all and which of the nodes. So sometimes starting and end is not a choice. Like he either starts from A, like that is fixed. This becomes the origin. Excuse me. And then from here, he has complete choice of where he goes. Does he go to B or D or should he directly go to F? So the idea is that eventually the salesman covers all the nodes with the minimum distance or the minimum time or the minimum cost, which is the parameter which is mentioned. So there are certain algorithms by which this is done. So this question is mainly talking about a traveling salesman problem. So now if the outcome of a traveling salesman problem is 1, then it is a vehicle routing problem. Does that make any sense? Is it a vehicle routing problem? Okay, so that doesn't make sense. The statement itself doesn't make sense because a traveling salesman, essentially, if the distance to travel from A to B or the time taken to travel from A to D is 5 and C to D is 6, and then if this is 1 and this is 2, and then eventually when the salesman comes back, there would be a value. Now, if that value is working out to 1, then that doesn't mean that it's a vehicle routing problem. No. It can be a time, like within 1 hour you need to travel, something like that. But just because the outcome is 1, it doesn't. So this one is a wrong statement. It's not correct. Second one, vehicle routing problem gives a set of optimal routes for a fleet of vehicles. Now that's a correct statement because so when we discussed that vehicle routing problem, what happens is there are multiple vehicles starting from different locations. Now we need to route it in such a way that all the vehicles optimize their distance, like it's a collective optimization, so that within the minimum time all the regions can be covered. So it's like having multiple traveling salesmen, so each vehicle becomes a traveling salesman. So it's for a fleet of vehicles. So when you do that, that's called a vehicle routing problem. Multiple traveling salesman optimization together becomes a vehicle routing problem. So this is a correct statement. Vehicle routing problem involves a set of optimal routes for a fleet of vehicles. Now, our traveling salesman problem gives a single route that visits each point exactly once. Yes, that's a correct statement because that's what. So there's one salesman, he visits one point exactly once at a minimum distance or minimum time. Now, S, traveling salesman problem shows the maximum travel distance and cost for visiting fixed locations. No, it gives the minimum travel distance and cost for visiting a location. So this is a wrong statement. So that works out to P, Q, and S, which is option B. Okay. Somebody says option, okay, Q and R, sorry, yeah, Q and R, yeah, Q and R, which is option A, correct, yeah, Q and R, option A. Yes, let's proceed on to the next question. Match the type of solid waste collection system with the items in column B and choose the correct answer. So this is a very simple one. I think we can answer it straight away. Primary, secondary, and tertiary. We've already answered this. Primary, it starts from the from where does it start? From solid waste generator to a source. So this is one. Secondary, from a transfer station or from a community bin. So its secondary starts from a community bin or a storage facility, whereas tertiary starts from a transfer station. We have discussed this, so that is option A. Let's proceed on to the next question. Match the type of solid waste collection system with the items in column B and choose the correct answer. Door-to-door collection system, curbside collection system, and block collection system. So this also we have discussed. We can quickly answer this. Door-to-door collection, waste is collected from each generator. Yes. Now, curbside, the generator delivers the waste to the vehicle at the time of collection and have to walk to the collection point. Now, that is block collection. We have discussed when the generator walks a certain distance and gives it, then a person arrives to collect. That's a block collection system. Curbside is generator keeps the waste outside and then retrieves the container later. So that again works out to option A. Now, yeah, so this is what we saw in the lecture also. Door-to-door waste from the generator, block, curbside, and communal. We have already discussed, so let's proceed. Match the, okay, one sec, there's some delay. Yeah, match the type of solid waste collection system with the items in column B and choose the correct answer. Community bin collection and door-to-door collection. So community, okay, so there are two answers for each one. So and the options are enable segregated collection of waste, 24-hour availability, prevention of littering, and increased cost. So P, first one, it is community bin. Is it it enables enables segregated collection of waste. No, because it doesn't. Community bin does not do that. Door to door does that. So yeah, door to door does that, because then people segregate and then you take it, whereas community bin doesn't. 24 availability, door to door, it's not available 24 hours, because when they're coming to collect, that's when you're giving. Whereas community bins are always there. People can, whenever they want, they can go and throw. So community bin is 24-hour available. Now the next one is prevention of littering. That comes in door to door, because they're storing it and then giving it off. But in a community bin, it can lead to littering also, because around the community bins, usually there's a lot of waste lying around. And increased cost is for door to door is more expensive than community bin, because you need to pay for the people who come. But again, community bin, you need a bin, so that cost, but compared to that cost, door to door is more expensive. So we have P has got P has got 2, which is 24 availability. That is the one for P. So P is 2 and Q is 3. So it is option C. Yeah, option C. Yeah. Okay. Let's proceed on to the next. Sorry, option A. Oh, it's the same. Oh, okay. It is Q. Q has got, yeah, it's option A, because Q has got all the 1 minute. P is 24-hour available. And this one is, okay, there's something segregation prevention. 1 minute. Door to door collection. Q has got all the three, and P. Okay, yeah. So I was right. Q has got all the three, and so here the options have been written wrongly. It was written P. That's why the confusion. Yeah. So this is the answer. What explanation was right? Yeah, the correct option is not there. Correct. Yeah. So there was a mistake in that question. This is the correct answer. I think previous one there was a small typing error. Q has got all the three, and P is two. Okay. Let's proceed on to the next question. Which of the following factors influence vehicle selection for waste collection? A similar question we have discussed. So here more options are given. Waste quantity, we've discussed, yes, that influences the vehicle. Frequency of collection, yes, because it influences the volume. Climate, and now street width. So street width, yes, because now the new option which has come is climate. So does climate affect or not? Yes, because based on the climatic condition of the region, we'll also have to plan what type of vehicle, whether it should be a closed vehicle or whether it can be an open vehicle, or the cart, the wheels. Is it a terrain with slip? Is it a slippery terrain based on the climate? So all of them affect. So A, B, C, and D, all of them affect the waste collection of the vehicle which is used. Now, problem 18. Which of the following statements are false concerning bin-less cities? So the first one, okay, I see a comment over here. Also, indirectly, the type, composition of waste is affected by climate. Yes, very good. Yes, the composition of waste is also affected. So, which influences the type of vehicle which needs to be taken. So, yes, that's also there. True. Very good for raising that. Now, problem 18. Which of the following statements are true concerning binless cities? A. Synchronized transfer between primary collection and secondary collection. B. A requirement for secondary storage bins at fixed locations. And C. Secondary collection vehicles are parked at fixed location. First one, A. Synchronized transfer between primary and secondary collection. Yes, that's what. So, what is binless city? So, which means that you have, so from the source, so this is the source to a intermediate station when we're taking, that is our primary collection system. Yes, Shweta says B is false. Yes, so let's come to that. Then from this point, when we take it to another storage facility, now this becomes secondary. Now, usually what happens is there is a bin kept over here. Now, for a binless city, how is this done? It can be, instead of a bin, it's a vehicle. So it's a vehicle which is there, and that vehicle now moves and then transfers. So there's no bin which is kept, but it's a vehicle itself waiting to transfer. So which means that from the primary vehicle to the secondary vehicle, there needs to be good synchronization. So the primary and the secondary collection systems are synchronized. So there's no bin, it immediately goes. Yes, binless, which means no stationary bin for secondary. So this is correct. Requirement for secondary storage bins at fixed location. So it's binless. So as rightly said, this is a wrong statement. Now secondary collection vehicles are parked at fixed locations, which is also correct because that is our secondary storage. Instead of bins, it's vehicles which are parked. So the false statement is B. So B is the answer for this question. Yes, yes, the explanation put is correct. The secondary collection is done in a larger vehicle itself. It's a mobile bin sort of. Yes, very good. So let's proceed on to question 19. Transfer stations are required when? Three options. We have discussed this already, so I'm not even reading the options. You can tell me what's the answer. A. Cost of direct haul to disposal and treatment site by the secondary collection vehicle is greater than the cost of haul to the other, installing a transfer station and transfer to the transfer station and transfer to the other region. So all put together, if this cost is if this cost of directly transferring is more, then we will put another transfer station. Yes, yes, you may ask your doubt. Right. Yes. Yes. No, no, no. That's a very, very valid point. Yes. So it is yeah. So by saying that secondary collection vehicles are parked at fixed locations, it doesn't mean that these locations are fixed throughout the year or it's always that particular location. Here the fixed implies that it's a planned location, that it is there. So that planning it keeps changing based on the quantity of waste generated or based on the time taken from a different region. So we have discussed that with time the whole composition or the whole routing and rerouting needs to be done. So the idea is that you route it and you synchronize it and you plan certain locations where this transfer happens. So here that's all that's implied. It doesn't mean that it's always fixed. Okay, right. So let's go to the next question. Cost of haul. So yeah, in the previous question we discussed about cost of haul of the of directly transferring from the secondary to the disposal site. So we've been discussing about cost of haul. Now, what does cost of haul comprise of? That's this question. So A, running cost of vehicle plus cost of manpower plus capital cost. B, running cost of vehicle plus cost of manpower. C, cost of manpower plus capital cost. And D, running cost plus capital cost. So A, running cost, manpower cost, cost of capital cost of vehicle. Yes, it is the correct answer. A, because all of them, manpower, everything comes under cost, haul cost. Yeah. Problem 21. Which of the following factors affect door-to-door waste collection system design? A, terrain characteristics, road network, population density, transfer station location, and capacity. We've discussed a similar question, so this can be answered easily. Affect door-to-door waste collection system. Terrain characteristics, yes, A, it influences. Somebody says C and D, okay, but terrain characteristics also influence the door-to-door collection system because based on the terrain of the region, we need to plan the vehicle which we are. So we are talking about system over here, which means it involves both the vehicle which is being used and the whole composition, routing, everything comes into that. Road network, yes, that also influences. Population density, yes, that influences because more population, more waste will be generated. Transfer station location capacity is also important because you're designing the whole routing and the vehicle fleet routing problem also is done under a whole system design. So all of them, it's A, B, C, and D. It's not just C and D. Right. Let's go to the next question. Match the following. Uh, different solid waste collection routing systems with their characteristics. So first one is traveling salesman problem, and Q is door-to-door collection method. So first one, optimal set of routes, and second one, Q, a single route problem, and three, no vehicle capacity limitation, and four, vehicle capacity limitation. So traveling salesman problem, optimal set of routes, a single route problem. So it is a single route problem, no vehicle capacity limitation, and vehicle capacity limit. So in a traveling salesman problem, are we talking about vehicle capacity in a traveling salesman problem? It mainly talks about the lowest distance, but there's also the fact that we are talking about one vehicle. So we also need to look at the capacity of that vehicle also. That overall capacity of that vehicle also needs to be considered. So that would be what P would be. Vehicle capacity limitation is also there because it's just one vehicle. Now, door-to-door collection, optimal set of routes, and no vehicle. Yeah. So door-to-door collection system, you will have multiple small vehicles going. So you can have optimal set of routes and you can have no vehicle capacity limitation. So that works out to option A. Yeah, option A, correct. Yeah. So this is the this one. So it's a single route problem. Now in a traveling salesman, yeah. So you're going. Okay, sorry. I think I mentioned it wrong. One second. Q. Okay. I'm sorry. In a traveling salesman problem, we are not looking at the. I made a small mistake in the previous explanation. In the traveling salesman problem, you're not looking at the vehicle capacity because you just need to touch all the points. Like the whole problem itself talks about that. So it doesn't have a vehicle capacity. Door-to-door collection is when you have the vehicle capacity because you're collecting it and then you need. So that one, that small mistake in the explanation before. So yeah. So that's why we can look over here. So there's no vehicle capacity in the traveling salesman problem, whereas in the door-to-door collection or the vehicle routing problem, and that's where in the door-to-door collection is where you have a vehicle routing problem where it needs to be taken, where we take the vehicle capacity also. One small correction there. Yeah. So let's proceed on to the next question. So this is the last question, and this is a traveling salesman problem. So we'll have to solve this. So we have not discussed this in the lecture. So I'll explain step by step. There are a series of steps which we follow while solving the traveling salesman problem. So here the question says a salesman needs to stop through cities A, B, C, D, and E in one route. He wants to find the most efficient route among these stops. Below is a chart of the cost for each of the stops. What is the most efficient route? So converting it to our vehicle routing problem, it can be a vehicle which needs to collect from bin A, bin B, C, D, and E. So this is one problem. Now, the cost is given. Now, it's already given in a matrix form. So sometimes a question can be where it's not given in a matrix form, but it can be just given to go from A to B, it is this much. To go from A to C, it is this much. But in whatever form it's given, eventually we need to make it into a matrix form in order to solve this. So the matrix goes like this, where we are giving M. M is considered to be like a penalty or a higher value because you don't want to travel one from A to A. There's no travel involved, right? So it's a penalty like or a very high value we give over here because our objective is to minimize or get the lowest cost. So M is a value which has a very high value. So with that we formulate this matrix. Now step one goes so first step says step one is to identify for each row what is the minimum value. So we first identify the row wise minimum value. So it goes like for A, so each row for this A row, 1 is the minimum value. Now for row B, 2 is the minimum value. C, 4, D, 4, and E, it is 1. It's there in 2 regions, so 2. That's step 1, identification. Now step 2 goes that we subtract the minimum value from each row. So from row A, we subtract 1. And then we write, and from row B, we subtract 2. So like that, we'll get a new matrix after this subtraction. So can we quickly do that subtraction? I'll just make another matrix. Yeah, so m will be constant. M. Now subtracting 2 minus 1, it is, yeah. So we are subtracting and writing 2 minus 1, 1. Then 4 minus 1, 3, 5, 0. Now this would be 6, 0, 4, 3, 5, 2. Yeah, 6. Yeah, 5, 2. Then this would be 0, 4 is what we are subtracting, 3. Then in this one, 4 again, 4 is what we are subtracting. So 8, 0, 1, 1. Now this is 1, 0, 2, 0, and 7. Right? My matrix correct, no? I can go wrong. So just check. Yeah. So that is step 2. Now step 3 goes that in each column, identify the minimum value. So whatever we did in step 1 for row, now we're doing for each column. So for column A, it goes that 0 is there. Column B also we have 0. C there is another 0. D 0, E 0. Okay. So our problem, half of our problems are solved. Now, if it was not 0 and if we had some other value like 1 or 2 or any other minimum value, we'll have to do this column subtraction also. Like what we did for row subtraction, we'll have to do a column subtraction and then get to new metric. Now, since it is 0, even if we subtract, we still get the same metric. So I'll just write. So step 4 is subtract the minimum value for each column. That is step 4. Now that is already done. Now comes our, so now we need to highlight which, but the lowest number subtracting is 0 only. Yes, so that's why we are not doing it over here. I just wrote it as a step, so it'll be the same metric. So we don't have to subtract. But it can so happen that if this 0 was somewhere over here, like in this 3's place, then in this entire column we might not have any 0, so we'll get some value, so we'll have to subtract it. If we're getting 0 in every column, then so our objective is to have 0 in both row and column. In every column there should be at least 1 0, every row there should be at least 1 0. That's why we're doing this. Why we're doing it? So that we get the minimum, like to understand which is the minimum path that needs to be taken. Now our second step is to mark these zeros for different columns. So for every row wise, sorry. Now, so it goes like row, column. So now we have done with the column 1. So now step 5 goes to mark the zeros row wise. So row wise, when we are marking, we also do something. I'll show that here. So let me just repeat this over here. The same matrix, I'm just rewriting it over here. M, M, 1, 3, 5. It was 0 over here. 6, 0, 4, 3, 5, 2, 0, 3, 8, 0, 1, 1, 0, 2, 0, 7. Yeah, this was the matrix which we had. So now for row 1, we are identifying where the 0 is. So it is located in E, in column E. So now we are striking off this one. So that's our first strike off. Now, and we have highlighted this. In row B, it is there in C. So now we are striking off this column. So you observe there is a 0 over here, but since we selected this, we are striking this off. Why? Because when we are doing the travel assignment from one region to one region, we cannot go, so yeah. So why we are doing this is because for a traveling salesman problem, there are certain conditions. So the first condition is that each vertex is is visited only once. You cannot in the previous one where we did the vehicle routing problem minimum distance, we saw that through the landfill you can go twice, like there was one option which said that. But in this one, are you selecting, okay, one sec, but in this one you're visiting only one, you're only visiting one, so that's why we're doing. There's a doubt, you are selecting row but striking off column, yes. So which means for this column, where is zero located? Because I've already taken that, which means A to E, like I'm having a small assignment or this is the lowest, shortest distance. So I'm striking off the column. You're absolutely right. We are selecting the row, but we strike off the column so that it doesn't repeat. Now just follow these steps. Last, you will understand why this is helping us. Now in the second one, we have selected this and we are striking this off. Why we're doing it? Because there's another zero over here, and by mistake we should not select the zero later, see that as a minimum value. So we need to remove that off. That's why we are striking this off. So this is a second strike. And now the third one, it's over here, so which means we are striking this off. So that's our third strike. And then we have D, which is over here, so we are striking this off. And now we have E over here. So now whatever we have got, these zeros, these are unique. So even though in E there are two zeros, now we have been able to take only this zero, select only this zero. That is why the strike off was used. So that even if there are multiple zeros, to select one unique zero from that. So now we have got a matrix like this. Now strike off is not important. The idea is we select these. Selection is more important over here. Now, after this selection, now comes our assignment. So since this is a bit cluttered, let me just redraw that once more. Sorry, 2. This is 2. 0, 7. Yeah, this is 2. Correct. So, so these we have already selected and kept. So it's there on this side, so I'm not drawing it here. Now comes our assignment. So we were in step 4, step 5, mark the zeros row wise. Now step 6 is our assignment. So coming back, so let's say we are starting from A. Now we assign. So first one, we are looking where to go next from A. Are we not striking column A? Yes, yes, we are striking column A. That's a last strike. Yes, we are strike. So as I said, strike was so that you don't repeat it. So that's why I didn't do it. The idea is that you are selecting these zeros. These are the ones which are selected. So now E is selected. We have already highlighted E. So now we can give A to E as the first one. So let's say we are going A to E. Now what happens is we select this one, E. Now you check. Now from E you need to go. So the one condition is each vertex is visited only once. Second one is all vertices are visited, that you cannot miss anything. All vertices are visited. And the last one is it should be a round trip. That means you start from A, you need to end in A. You cannot like if you start from A and then you say you're ending in E, that's not. It should eventually come back to A. So what happens now is you take E. Now for E also we have selected A, like we have selected the first one, which is A. So which means what will happen is you will go to A. So this is not an option because it doesn't justify, it doesn't fall under these condition because you're already getting a round trip and you are not visiting any of these vertices. So this one is not valid, it's not correct, so it violates this. So this is not possible. So in that case, what do we do? So we take the next least value, which is in A, because here we have a condition that you're starting from A. That's a condition that we are looking. So then we look at 1. This is the next least value. So you select this column. So now what we're doing is in this column, now we look again from B. When we're looking, it is not A, which means it's not for this row, if you look, the minimum value we have selected is in C. It's not in A. So it's okay. You're not immediately getting a round trip. So it's possible. We can continue in this path. Now, we remove out it from this one. We remove out all the ones, all the values from this column. We remove out all the values which are less than the value that we have chosen over here, or the value which we have over here. So we have 1 over here. If we had 1 or 0, anything less than that, we'll have to remove that. So 0, which means we are removing it out. Now, why we are doing this again? It's mainly so that we don't go, it's to condition this, so that we don't go back in the same loop. Towards the end, you will understand why, but to follow the steps, we cross that out. So we are not taking that. Now, so B is selected. Now from B, we can go to the next one. So we have A to B. Now B, what we have selected over here is C. So C, so that is selected B to C. Now what happens when we take C? Now this column gets highlighted. Now in this column, we need to now remove out 1 and 0, because we already have selected 1 once. So 1 and 0 is removed. We are striking that off. So now we are in C. Now we will look at C. From C, where will we go? So from C, we have already highlighted over here. It is D that we are going to. So D. So C to D. So now we take this entire column and then we see, is there any value lower than 1 or 0? There's no value, so nothing to strike off. So now D. Now we go to D again. Now from D, where do we go? From D, our value which we had was 0. But that 0 we already striked off. Now, what? So we choose 1 over here. Now you see why the striking off was important, because we had already visited B. So if this was not striked off, we would have immediately gone to B and then we would have ended up in the round trip without touching all the vertices. So that is why we do this strike off. So now we have 1 over here, which is the next value. So we take 1. So we select E. So which means from D, we will go to E. Right. So now in E, we will see whether there are any values. So 0 is there, which is less. So that, yeah. So in this one, we have already taken. So now in E, we know that so E is there. So E, this one, yeah, this we can strike off. It doesn't matter. Now from E, there's 0 over here. So which means we will go to A. So that is A. So now, yeah, so we have finally found our round trip. So that's A to B to C to D to E to A. Right. Can you please repeat the striking off method again? Yeah. Are we not striking the column A? Uh, yeah, we did. Okay. I'll just explain from this one onwards. Uh, yeah, I'll just repeat it. Or maybe I think I have it in the slides here. Yeah, I mean I've put it down here, so it would be so yeah. This is so this is what I explained. So I'll just repeat it. So I'm not drawing it again. I'll just repeat it with this. So the whole process I'll just repeat very quickly. So first one, from this you are identifying the row values. So it's highlighted over here. The row minimum have been identified. Now row reduction, which is step 2, where we will reduce all these values. So when you're subtracting 1 from all this, so this becomes 0. So 1 minus 1, 2, 4, 4 becomes 3. So like that we are getting this matrix where we are subtracting. So that was row subtraction. Now we take column. So for each column, we identify which is the minimum value. So that's identified over here. And we have zeros in all the values. If you don't have zeros, we'll have to do a column reduction also, where you subtract the value that you're getting so that zeros come in each column. So now that we have zeros, we are stopping it there. So now we do row scanning, which means we are identifying each row which has got zeros. So for row 1, we have identified it over here. After we identify that, we strike off that column. After we identify that row, we strike off that column. That's what is shown over here. Now for B, we are identifying 0 over here. Now we are striking that off. C over here is where we are identifying. So 3, so we are striking that off. Now for D, we are identifying it over here. So we are striking that off. And for E, it's in column A. So we are striking that off. So everything is striked off. So why we are striking off is so that we can highlight these zeros, or we can identify these unique zeros. So if you observe, there's another 0 over here, but we are not selecting that. So to select, that is why we are doing the strike off. And why we didn't select? Because we had already striked it off in 2. So when it came over here in E, the only thing which is remaining is this 0. If we had not strike this off, we would have been confused on what to choose. That is why we are striking. Okay. Now the next step 6 onwards, we are starting with the assignment. So first one, we are checking. So these are the highlighted values which we had. So based on these highlighted values, first one we can assign A to E. If we do that, then the next one will be from E. Where will we go? So E also, the 0 that we have is over here, which is this one. This is what we had selected. Remember, this one we had not selected because it was already striked off. So then that would already be a round trip and we will not cover all the vertices. So this is not possible. So we are going for trial 2. So instead of selecting this 0, we select the next minimum value, which is 1. Now after we select 1, we select, so it is for this row that we selected 1. Now we select that particular column also, and in that column any value which is less than 1 or less than 1, we strike that off. Because why? This is the minimum value, so we don't want to have any other minimum values over there. So because of that, we are blocking 0. So that is striked off or blocked, which is shown in red. Now, since this is B, we are going to column B. So in column B, which is the next value, so we have got 0 in C. So again, this is from the highlighted value. So we have it in C. So C, so now we highlight the C column. We are highlighting C. And then we are looking for values. So there's 1 and 0 in C. So we strike off those also, which means you're blocking those. That is also blocked or strike. Then we go to C. So this one is A to B to C. Now from C, where are we going? From C, we have got 0 at position D. So D, but in the column D, when we look, there's nothing to strike off because all the values are greater than 0 or greater than 1. So there's nothing to block or strike off. So now we are going to D. So in D, the one which we can go is the minimum value which is there is 1. So there are other values also, which is this 0 and this one, but those are already striked off or blocked. Why? Because we have already gone to those vertices. So that is why we strike them off. So we don't want to go again. So now we choose this, which means we are going to E. So now from E, the value which is there is this 0 because this is already striked off or blocked. Now we have got this 0. So which means we will go to A. So A to B to C to D to E. Okay, is that clear? Yes, no? Any doubts? Okay, so that's all. That's all I wanted to discuss today. If you have any doubts, it will take some time to sync. Okay. Yeah, anyway, this presentation would be shared so you can take a look at it later. And don't worry, this traveling salesman problem will not come for your exam for this particular exam traveling because it involves a lot of calculations and all. This will not come for your exam. But since we were discussing about this, I thought we'll discuss the method of how do we do an appropriate vehicle routing problem. So it's okay, but it's good to know because this is usually used in all optimization methods. For instance, if you want to plan in construction management, this is used where you plan different tasks. So the time taken to complete different tasks are given or to collect from different regions are given. So with all that, it'll be useful. There are a lot of applications of this traveling salesman problem. It's a typical problem. So here we discussed it because for vehicle routing that's been used. There are many other applications also. What is the name of this technique? Uh, this is okay. I do not know whether there's any other name for it, but this is the metrics way of solving traveling salesman problem. Uh, I don't know whether there's any other particular name for that. I'm not sure. Okay, right. So, any other doubts or regarding this week or previous weeks? Yes, so I was explaining the doubt which was discussed in the previous week. So, Ranjan, I think you got logged out exactly at that time. You had asked a doubt at in the beginning. Oh, sorry, last week. So in the beginning, I was explaining. I think this is what your doubt was, right? About this slide. Am I correct? Okay. Okay. So, yeah, I hope the explanation was okay. So we take the minimum 10 kg. That's what we usually take. Right. So if we have no doubts, maybe we can wind up today's session. I'll be there for another 10-15 minutes. If you have any doubts, you can come back and then ask also. Otherwise, yeah, so thank you all for joining. See you all next week. Bye bye. Good night. Okay. Can you please explain plus or minus edge-weighted graphs discussed in lecture 24 in next session? That's what's there in the in week 6, is it, or week 5? Lecture 24. Lecture 24 is oh, lecture 24 is this time only. Okay. One sec, let me just check that. Lecture 24. Oh, you're talking about positive, negative, edge-weighted graphs. So that's what we solved today, right? For using the Dijkstra's algorithm, we solved, yeah, week 5. Yeah, today we solved a similar question, right? Single, I think that's what you're talking about, no? Uh, yeah. So can you please explain? Okay, what is positive, negative edge? Oh, okay, okay. Positive edge weight graphs, no? Yeah, so by okay, okay. Why is it positive and negative? Is your doubt, right? That one. Yeah, so that I'll clear that in the next class. Maybe let me just check whether I have some notes on that that I can just. So I mean, positive is easy. Like that's what we did today. So you add up. In negative, to give a good example. Oh, okay. Hello, Greety. But we're almost done with today's class. I guess you missed today. Let me give you some examples of negative. Yeah. So for the one which we did today, that was it was a minimization problem where we had to minimize the total cost or distance or time. So when you go from one point to another point, it kept adding up. So that's a positive edge, like you're keeping on adding. Right. Now, that's a positive edge. And this algorithm which we use, the Dijkstra's algorithm, is used for positive edge. Now, a negative edge can be when you have a negative value over there. For instance, if you're traveling from A to B, you need to you need to pay a fine of 10, like you need to pay 10 rupees. Like imagine that's the case. Uh, so there, if you keep adding, and if you want to travel from B to C, no, payment. No, if you imagine you have a fine, like it's a path which you should not have been taken. Like, so there can be positive and negative. You go to one region, you get 5 rupees. If you go through another path, 5 rupees is taken from you. So now that becomes a negative, like it'll be minus 5, and the other one would be plus 5. So in the same routing problem which we had, let me just share my screen. Yeah, so in this same routing problem, if traveling from A to, so these are all positive values. So from to go from here, imagine this is the amount of money that you would be spending. So you have so if you go from this region, you get 5 rupees because you're making some profit out of it. Imagine that. And if you're going this direction, you lost 2 rupees. So what happens is eventually, and this is again a loss. So in this node, if I'm taking this, eventually I will have 5 rupees with me. Imagine this is plus, like you gain 5 rupees. So if I'm going this way, first I'll have a loss of 2 rupees and then I'll have a gain of 2 rupees, which means when I'm coming over here, it is zero. So fine can be added in the cost, right? Yeah, but it can also be negative. Imagine this was negative, it becomes negative. So uh so you can have a positive and negative values also. So that's the, what you say, positive or negative uh, edge, you say. So again, it can be a minimization problem, it can be a maximization problem. In construction management, we usually have this NPN networks and all that, node point node, PN point node. Those networks, that's where all these negative values also come. For instance, if you're not being able, so there'll be multiple constraints like just cost and time. Along with that, some other constraints will also be there. So in like material constraint, like it gets over, a capacity becomes a constraint. Like you go from here, your capacity. So you need to add more capacity if you're going this way. So when all those constraints come in, you can have something which goes in the positive direction, something which goes in the negative direction. So that's where you have the positive and negative edges. Constraints can be taken as negative. Yeah, constraints can be taken as negative also. Yes, it can be taken as negative. But okay, yeah. With this Dijkstra's algorithm, whatever we discussed, it's mainly for a positive edge where you keep adding on. If you have something which is being subtracted and all that, then or a fine or loss and all that, or you take this, you have a discount. So those are additional features which are coming, right? Negative. So that in this algorithm we don't follow. Maybe it doesn't give the correct value if you're following that. Okay. हाँ दादा हाँ रहेंगे Okay, so if there are no more doubts, I think we can call it a day and wrap up for today. See you all next week. Bye bye. Have a good night.